Okay, I'm double broadcasting right now. I'm verifying that YouTube looks like it's streaming. YouTube looks like it's streaming to me. Now we're going to go into Inception mode. Now we're going to go into Inception mode. It is Friday, March 5th. It is Friday, March 5th. It is Friday, March 5th. Let me stop double broadcasting. Let me stop Inception. Let me stop double broadcasting. Let me stop Inception. And that's the end of double broadcasting. Okay, we are broadcasting on YouTube. I am in game by the Granville Conference Center, and I am at Westmont campus in real life. It's a beautiful day out. I'm running through the checklist here. I'm over by the front of the auditorium with Dodger. Let's run through our checklist. Make sure you've got the VPN activated so that we can do audio if needed. Let's find a quiet location and tell your roommates you need to stop your choir practice while you're on class. Turn off notifications and any other things that are making noise. Turn off notifications on your computer. Let me do that. And on your phone or watch or tablet or eyeglasses or whatever you've got that are making noises. If your firewall complains, allow your firewall to get through. All right, so no notifications. Put on your headphones so that we don't hear echoes when you talk. We really can hear echoes if you talk and you don't have your headphones on. Everyone thinks they can get away with it, but we can hear it. Shut down any extra apps or browser tabs that you got open. I'm running through mine. I'm looking to make sure everything I've got is relevant to teaching today. Nope, that's not everything. Let's get rid of that and get rid of that. And if you have any extra browser tabs open, a lot of times browser tabs take a lot of CPU power as well, especially kind of ones that are running applications. Oh, shoot, just got rid of one I didn't mean to get rid of. Especially ones that are running applications. So it turns out Canvas seems to be a pretty heavy hog, and Google, like Gmail applications, are pretty big resource hogs as well. So I shut down all but one. Do have at least one Canvas window open though, so you can reflect on what we have to work on and where we are in the schedule and what the content is that we're doing. Open up Eclipse and connect to Saros. I'm currently on Saros. I see several of you there. Oh, you're on top of it today. I'll go ahead and start sharing while we run through the rest of the, while we run through the rest of the checklist. Here's the class for today. And I'm going to send out the share. Share. Boo, boo, boo. There we go. Next. What if I hit this one? Does it work? Does not work. Okay. I don't know why there's a big check at the front top of the list if it doesn't work, but so be it. Move on. All right, so you should be getting a project for class 23, March 5th, which is today, and it has a hello world and a little bit of stuff from yesterday. Okay, open Firestorm. Hopefully you're here already, and rebake your avatar. So go under Avatar and Avatar Health and Force Appearance Update to make sure you come in. Go under World and make sure we're in midday. So World and Environment and midday looks good. Go to our classroom, you're here, make sure you can see your classmate's name and check in at the attendance machine. And if you want to, check audio with a friend if you're so inclined. I should set up a little area where we have isolated sound so that you can do that without talking to the rest of the class if you want. But looks like we got a pretty good turnout today, a few missing. So if those folks who are not on the board right now are in class, please come over to the attendance machine and check in. Dodger's here as well, but we'll have him lay down and be quiet for the rest of the class. There you go. All right, let's see. These are still announcements from last class that are up here. All of them are relevant. No, they're not relevant because we do not have office hours here. We do not have office hours tonight with Josh. So let me update that. And so 3.5, no particular announcements for today. So I'll just set that up. All right, so you should see the announcement board reset there. And fax machines are good. Let's see who we got in class today. Luke, Monty, good morning. Bernie, good to see you. Morgan, hello. Ben, good morning. Josh, good to see you. Animating without intent. Landon, good morning. Faith, good morning. Ethan, looks good. Adeline, Dee Dee, good morning. Thomas, Sam, Trent, Ethan, Ben A. and Ben Fernberg. Good morning, everyone. Good to see you virtually. Thinking next week we need to do some kind of theme in game. Maybe I'll go find some Hawaiian shirts or something so that we can celebrate the week before spring break. Maybe I updated my outfit because I was getting a little sick of my other outfit, so I put on a leather jacket because that's how I'm feeling. All right, let's check in and see how we're doing on sharing code. All right, let's see, progress, swimming. And let's go through and do some read-onlys. Adeline going to read-only. Ben A going to read-only. Ethan going to read-only. Landon going to read-only. Luke going to read-only. Monty, sorry, Monty. Dee Dee going to read-only. Sam going to read-only. And Thomas going to read-only. And we'll check back in as that settles out here in a sec. We'll give try and add folks who weren't there the first time, or I didn't notice, or restarted, or something. Not sure. All right. All right, that brings us to class today. We're ready to go, I think. Just to open us with a word of prayer. Dear Heavenly Father, thanks for a chance to learn, use the gifts and abilities that you have given us, and to develop new gifts and abilities with meta gifts and abilities you've given us to learn and to grow and to develop a passion for changing the world in particular ways. I pray that you would work in us as we learn what it is we're excited about and give us the tools to realize that in the world. Amen. All right. Look at the calendar. All right, on screen, I'm going to broadcast a version of the calendar that we've got on Canvas just to reiterate where we are. It's Friday, March 5th. We have a week ahead of us. A week from today, we have an exam up through and including the work that we're doing in chapter 15, so including Java Collections Framework. Let me make sure that's consistent with what I'm saying in the exam notice. Yeah, that's just a placeholder for now. Okay. Where'd my calendar go? Shoot, I got rid of the calendar. All right, we've got some work on chapter 15 coming up, and we have a programming assignment due next week as well. No need to slow down at this point. Let's take a look at what that looks like. All right, so what's coming up for next week's programming assignment, and you might want to get started on it over the weekend, is to create a polynomial class, and it's going to store a polynomial. Polynomial is a math equation, and it's going to be a single variable polynomial. And so what you can see here is you can see that this first equation is an example of a polynomial. And what characterizes a polynomial is that it's a sum of several different terms. In this case, you can see 5x to the 10th and 9x to the 7th and minus 1x and minus 10x to the 0. That's the last one. And each one of these you can think of this as being a list of terms. It is a set of terms where you have a coefficient and you have a power. So you have 5 and 10 in the first term, and 9 and 7 in the second term, and minus 1 and 1 in the third term, and minus 10 and 0 in the fourth term. And so if we wanted to take this mathematical expression of a function that is a polynomial, we can represent it as a list. And we could represent it in any of the different list formats that we know about, linked list or array list or any other ones we know about. But what I'd like you to do is to use the Java Collection Framework class, linked list, to create a list of elements that can represent polynomials. This is a list that contains 4 elements. The elements are each pairs. So 5, 10 is first element, 9, 7 is the second element, minus 1, 1 is the third, and minus 10, 0 is the fourth. Because each one of the elements in the linked list is not a primitive type, It's not just an integer, it's not just a double, it's not just a string, it's not just a Boolean or any of the other ones we know about. You're going to need to create a second class in addition to the polynomial class. And the second class will be a term class. The term class is pretty simple. It just contains two instance variables, an instance variable for the coefficient, for example, 5, and an instance variable for the power that x is going to be raised to. So in the first case, the term class has two instance variables, private instance variables, coefficient and power, 5 and 10. So I have some skeleton code for you that you can download and complete. And you need to complete it so that you create a constructor that can create a polynomial. So you're going to create this polynomial class, and when you call the constructor, what it needs to do is keep track of a linked list internally. And so the constructor needs to initialize that linked list, needs to call the constructor on linked list, new linked list, and store it locally. And the constructor is going to take a single term. So when you initialize and you call your polynomial, you will pass it in one term. And so as your constructor internally in polynomial is creating a linked list that's going to be encapsulated in the polynomial class, it will start off that linked list with the term that's passed in the constructor. Then I'm asking you to do three things. I'm asking you to create methods, well, a little bit more than three things. I'm asking you to create methods that will enable you to add two polynomials. So that means that I'm asking you to create a method in the polynomial class called add that will take in as a parameter a second polynomial. So you have two polynomials, the one on whom you are calling the add method and the one that's being passed in as the parameter. The structure here is a little bit like the withdrawal function in the or the transfer function from bank accounts, where you have one class that is receiving a second class as a parameter. When you add two polynomials, what you do is you take all of the terms that have the same power, and you add the coefficients together. So this is going to require you to loop through the linked lists in both of the polynomials to combine terms. When you multiply polynomials, you have to take every pair of terms and you have to multiply them, adding their powers and multiplying their coefficients. And then after you've done all pairs, you have to go through and you have to reduce all of your duplicate variables that have the same power so that you only have one of each power in your linked list, meaning you don't want to have terms that are like 5x to the 10th plus 3x to the 10th plus 1x to the 10th. Those should all be combined into 9x to the 10th. That's what I mean by part 3 here. A polynomial is always reduced to the least number of terms, and there are no terms with a coefficient of 0. So as you're going to have to write a helper method in your class that will pass through your linked list and will combine any terms that have the same power in them, and will remove any terms that have a 0 coefficient. So as we look at the code above, or the equation above, and the skeleton code that you're given, you'll be able to create that coefficient with code that's a little bit like what we see below. P1 is a new variable of type polynomial, and we will call the constructor by passing in a new term, which we're also creating on this line and then just chaining right in. That new term is taking the coefficient minus 10 and the power 0 to create the 10 here, the 10 at the end of the equation. What returns from that constructor is a polynomial P1 that has one term in it. Now, if we want to add another term to our polynomial, we need to add two polynomials together. The polynomial that we had previously, P1, that had one term, minus 10, and we're going to add a new polynomial that has one term as well, minus x to the power of 1. And you can see that we chain together two different constructors and then pass them into the add method in order to have a second polynomial to add to P1. That polynomial is the polynomial that gets chained in and passed into add never gets a local variable name. We could do each one of those constructors separately in between the line that defines P1 and P2, and we could introduce local variables that hold references to new term minus 1, 1, and we can have another local variable that has a reference to the polynomial that's being passed into the add method, but we choose not to because we don't need it anymore after we add it in. And instead we capture a reference to the polynomial that's returned by the add method, P2. P2 then will have two terms in it. It will have a polynomial with the term minus 1, 1, and the other term it will have in it, embedded within the polynomial P2, will be a linked list that will also have the term minus 10, 0. We follow that same pattern by adding to the polynomial P2 a new polynomial with another term, 9, 7, just one term. Gives us P3, a polynomial that will have the three terms 9, 7, minus 1, 1, and minus 10, 0. And then finally P4 will add our fourth term, 5 times x to the 10th, as you see in the fourth line there. So then when you want to do something like compute the mathematical expression px times px, you can do that with a second method that you're going to implement in addition to the constructor and add. It'll be multiply. And here's an example where we take P4, the polynomial that we created above, and we multiply it by itself by passing it in as a parameter, and we return a fifth polynomial, Q. And then finally, we can print out Q using a print method that we devised to print things out in a polite way, or in a pretty print way. Also, in the skeleton code are some JUnit tests that are structured there for you. And I also would like you to make sure that you write JUnit tests for your own code. And I want you to try and achieve I guess I want you to try, in order to get credit, and I also want you to try to achieve it, you need to get 90% coverage of your lines of code in your JUnit tests. That means you need to write enough JUnit tests that when you run the entire suite, you'll see that there's 90% coverage in Eclipse. I'll show you where to look for that in a second. You'll turn in 4 files: polynomial, the implementation of the polynomial class; polynomial test, implementation of the JUnit tests; term, an implementation of the term class, polynomial will use that; and then term test, which has JUnit tests in it that test the term class. More or less, this is based on problem P15.3 from the textbook, but I felt like the textbook didn't do a very good job of specifying some ambiguities in the particular problem. So I added additional constraints and changed the way in which some of the methods were called, but just to give credit where credit is due. All right, sounded like there was maybe a question. Let me see if there's a question in game. Nothing yet. Okay. So let's see. Let me solicit questions if you have any questions about that. And while you're thinking about that, let me go through and make folks read only. And then what I want to do is show you how to do JUnit tests such that you can get 90% coverage. Okay. All right, looks like we're okay. Morgan, we'll try one more time. All right, what I'm doing is I'm dropping the skeleton code into our project for today. And hopefully you all will get a copy of it. There we go. And so great, here's the polynomial class. You can see that it's stubbed out. I've done the design work for you. I've created a public interface. I've given you comments for most of the methods, and I have given you a bunch of to-do elements so you know where you need to do work. All right. Term is the same way. Term, I've provided you a structure for the class, including an instance variable called coefficient and a power variable called power. I've made them integers, although technically speaking, they could be doubles, but just to keep this assignment not too nuts, we're going to treat it as integers. And you can see that there's some work that's laid out for you here. Some of it's done, some of it's not. When you go and you want to test out your code, you'll need to use a JUnit test. And so here's an example of a JUnit test for the term class. You can see that it is a test it's indicated as a test for JUnit to run by adding this decorator to the front of the method. You put that before the method. And when you do that, JUnit will know to run this as a test. And you can see that this test called test something is going to fail no matter what because it has this automatic fail line in here, not implemented. On the other hand, here is a test that tests something else, and this is going to end up being true, even though it's kind of a worthless test because it's going to pass, but it's not helpful because what this is going to evaluate is that 1 equals 1, and that is true, but it's just not helpful. But the reason why I want to show you this is because if you right-click on term test and you run it as a JUnit test, as we've done previously, and I'm broadcasting okay. Let me make sure I'm broadcasting okay. Yep. You can see that it passed one test. I double click on that test in the bottom left and it shows me the test that it passed because it's green down here in the JUnit test results. Another test failed. It's the dark blue here, and I double click on that and it'll show me which one failed. It'll show me which line it failed at. And if I want to see the full stack trace, I can see the stack trace here under failure trace to see exactly where it failed, but that's kind of straightforward because it says fail. The part where I was saying in the assignment, I asked you to make sure you had 90% coverage. What I'm interested in seeing is this coverage page here filled out. Now you won't see any results here unless you run this, you do coverage as a JUnit test. This is going to color your lines indicating which ones have been run, and then you'll get a coverage indication. And so if I load up my term class here, you can see, you can sort of expand this here. Let's find, here's skeleton. So I'm gonna, when I look here at term, what I can see is that there has been 0% coverage of this class, meaning that in terms of lines of code that I have written in the term class and testing that I have done, 0 of the lines of code have been tested. And I can drill all the way down to all these different lines here. I want this number to be 90. And the way you're going to get that to be 90 or greater is by adding additional tests. So term test here. So what one thing we could do is we could just test to make sure that the coefficient that the constructor works. So what I could do is I could add to test something that says term t equals new term, and we'll give it numbers 3 and 4 for 3x to the 4th power. And then we can, and then we can just run a simple test that says assert equal, and we can say we think 3, and we think t.get coefficient. So if everything has worked correctly and we've called our constructor well, I'm going to have to import this class or import this test. There we go. We expect the answer to be 3 when we call t.getCoefficient after we've just created an object where we've passed it 3 and 4. This seems obvious, but what we're doing here is we're checking to make sure that our constructor and our getCoefficient are working correctly together. So now when I rerun my code coverage by hitting my JUnit test button over there, hitting OK to save, getting new coverage, you can see that something new has happened. Down here, when I look at my term class, it has gone from 0%, oh, didn't mean to expand it to the whole screen. Down here, when I highlight term, I can see that now my coverage has gone from 0% to 14%. That means that I've written tests that have covered 14% of the code. And as I drill down, you can see, well, that means that I've covered 0% or 100% of the constructor and 100% of getCoefficient, but 0% of these other 3 methods here. So the goal is for when I select polynomial class to see that 90% overall has been covered there. All right, so that's what I mean by coverage. In order to tackle this, you may need to review polynomial math, make sure you understand what the results should be. You may even want to write some tests before you begin your code to make sure you understand how the code's supposed to operate and what polynomial math addition and multiplication does for you. That way you know what you're shooting for. So kind of like our quadrilateral assignment, this is similar in the sense that you have both need to understand the math and you also need to understand the implementation. And so I felt like in the quadrilateral class, actually the class did really well on writing the code and doing comments well and having good structure and like things like spelling checking and indentation. It all looked really clean. But it wasn't always good in terms of the actual task that you were trying to solve. Like not all the quadrilateral work ended up being accurate. So both those things are important. It's important that your code is beautiful, but it's also important that it's functional. So those are two things to think about in this upcoming assignment. I'm going to switch back to Java Collections Framework, but let me give a second to answer any questions. I'm going to go in game for a moment. All right, broadcasting on YouTube. All right, so now let's switch back to talking about our content from chapter 15. We last left off talking about our linked list, and we looked at some of the different ways in which we could use our linked list, and that should still be present in, let me make that go away, that should still be present in our code if we go under last, did I put that in, wait a second. Yeah, that's all good. All right, I didn't mean to have these guys in here. What did I mean to have in there? I felt like I edited this, but maybe it didn't take. Or maybe, I don't know. I don't know what happened. The code wasn't quite where I had it when I started class. All right. Wow, that wasn't what I wanted to do either. Go back. I want Java collection framework there. I want brokerage, Robinhood, stock to go away. Go away. Okay. Hello world can stay there, but I want it up one. Okay. Better. And let's just make sure nothing broke there. I'm going to run it. All right, there we go. All right, that's kind of what I want the state of the world to look like. All right, so when we were looking at the Java collection framework last time, we tried a bunch of things. We ended up looking at a hash map and looking at some of the functions with that. We also were looking at our linked list and our array list. Here's an example of creating a linked list with the constructor. Here was an example of us adding different things to our linked list. And then down here, we had the ability to cycle through our linked list using a fast enumerator with the colon notation and the range. The variable on the left, the colon, and then the collection that we were ranging over. So the reason why we're able to use fast enumeration, the reason why we're able to do that loop is because our collections implement something called an iterator. We can do a fast enumeration over any object that implements an iterator. So if you end up wanting to create your own your own collection, you'll be able to do fast enumeration over it, provided you implement the appropriate classes, the appropriate methods in it. And one of those is the list iterator class and method. So we use a list iterator in order to access elements inside a linked list, like you do when you're looping through the elements. The idea is that a list iterator encapsulates a position anywhere inside the linked list. So the idea that an iterator is trying to encapsulate the object, what it's representing is a position within the list, like a cursor in the middle of a sentence in a word processor. The iterator is a concept like a cursor in a word processor, except that it's a position in a linked list instead. You can think of it as pointing to the space between two elements, just like if you have a vertical bar cursor going in your word processor instead of a fat block cursor. In order to get access to an iterator, we can use a method that's present in the linked list class. Now, the linked list class has a particular iterator called a list iterator. For example, in this yellow box, if we have a variable called employee names and it is of type linked list with a string as its generic contents, we can also get an iterator called list iterator, also with a generic type of string because it's going to iterate over a list that has strings in it. we'll give it the variable name iterator, and we'll get a reference to it by asking our linked list to produce its iterator. So one of the things that a linked list can do is it can produce a cursor that walks down the list. Once we have a reference to that, we're able to use it to move around our list. It's also a generic type. All right, when you first start out, the iterator points to the position before the first element. And you can ask the iterator if there is a next element by calling the method hasNext on the iterator. Now we actually have two objects here. We have the list itself and we have the iterator. These are both references, but they're working together talking about the same linked list collection. And so when we say if iterator.hasNext, what we're asking is, are there any more elements in the list after the position that our iterator currently points to? So after we call the method for the first time, the iterator is initialized. It begins at the beginning of the list. And if the list is not empty, iterator.hasNext will return true or will return true. If the list is empty, it would return false because there's nothing after it. If we have ascertained that there is a next element, we can then call iterator.next. And this is like hitting the right arrow key on a word processor. It steps over one element in our list, moving the cursor from the beginning of the list to the position between the first element and the second element. And as you're calling the next method, as you're hitting the right arrow, if you're thinking about it in a left to right language sense, as you're moving over that first element, the next method will return the element that it passes over. You're iterating through the list, passing over elements and getting a reference to it. It doesn't change the list, doesn't do anything to the list, it's just examining the list element by element. And so this yellow box here, this is sufficient to iterate over the entire list. Oh, no, that's not right. If it was a while loop, it would go over the entire list. As an if statement, it's only going to look at the first element. If that if had been a while, it would traverse the entire list. All right, so when we call that next method, it's going to return the element that the iterator is passing over, and the return type of next is going to match whatever the generic type is that's in the diamond syntax, the angle brackets. So it'll return a string if we follow the code from the previous slide. All right, so here's an example of going through all of the elements in our linked list. We change that if statement to a while statement, and in that first yellow box, we can say while iterator.hasNext, meaning while there is another element to step over, we will do this code. We will create a local variable called name that will hold a reference to the element that we're about to step over. We call iterator.next. Iterator moves from one position to the next and returns the element that it passes over. We can examine that element of the list. We'll examine it by using the variable name, and then we can do something with it. We can check to see if it contains a keyword. We can check to see if it is above a certain value. If it wasn't a string, it was a double or something. We could, if it is like a country, we could check to see whether the population is a certain level. If it's a DNA strand, we could check to see whether it encodes certain proteins that we care about. There are all kinds of things that we could do. The idea is that we're iterating over a collection of data. Once we have these iterators in place, we're able to use this shorthand fast enumeration syntax in order to do the same thing. So the first box and the second box are going to do the same work, assuming that iterator came from the collection employee's name. And what that fast enumeration does is it calls those iterator methods for us. And so this is shorthand. This is shorthand right here for calling, getting an iterator from employee names, saying while iterator.hasNext, and each time you go through the loop saying name equals iterator.next. This is all done for you automatically. This is a process called, ready? Syntactic sugar. Like sugar, the food that you eat that's sweet, and syntax like the structure of a language. It's called syntactic sugar. And that's a fancy programming languages term for a shortcut that isn't really adding any additional power to a language. It's simply making it easier to use existing power. And so this fast enumeration is a way of using this underlying structure to make things go faster. when you're coding. And so if you wanted to create a collection and you implemented an iterator method and then the iterator has next and next, your collection could also do fast enumeration as well. It won't be able to out of the box though. Okay, so to work, in order to work, a couple things have to be true about our linked list. Now we're thinking in terms of a systems implementer for the linked list. We know people use the linked list. They use it like they would use a list, keeping track of elements, but we're now thinking about what would it be like to implement a linked list. And to do that, what we would keep track of is we would keep track of two links for every element in our linked list. One that points to our next element in our list, just like people holding hands at the beach, and the other pointing to the previous element. And because we have a link forward and a link backwards, we call that a doubly linked list. If it was just forward, it would be a singly linked list. But we have forward and backward, and that makes it a doubly linked list. That makes it easier to move forward and backward for our list iterator. To move our list position backwards with our iterator, we can call hasPrevious and previous. And these are analogs to hasNext and next. Sorry, I went a little fast on that. Our iterator doesn't just have to go forward, it can go backwards. Just like a cursor in a word processor, you can use the right arrow or the left arrow. You want to check to make sure there is an element to go backwards over by checking hasPrevious, make sure that's true before you call previous, and hasNext before you call next. But as you step over, you'll return the element that you're stepping over with either previous or with next. So you can move forward or backward. This iterator, because it's a position within our list, gives us the ability to add and remove elements from within our list. So let's say that we start with a linked list that has 4 elements in it, D, H, R, and T. And these will be shorthand for names like Diane, Harry, Romeo, and Tom, if I remember correctly. So when we start with our iterator and we ask our linked list to give us an iterator back, that red line represents where the iterator is currently referencing. And when we call next, the red line steps over the D, and the result of calling the next method is to return D, or Diane, the name Diane. If we call next again, we would return H, but we're not going to. Before we call next, we're now going to call add, not on our list, not on the list object, but on the iterator object, which is a cursor in the middle. And if we call add on our iterator and we pass something in, it will insert something before the position of the red line in our list. Now remember, we have one list, but we have 2 references to it. One, which is the overall linked list reference, and the other is the iterator. They're both working over the same data, but they're doing different things. The iterator is a cursor, and the linked list is capturing the whole thing at one time. If we call add on the reference to the whole list, it's going to put something in at the end of our linked list. If we call add on the iterator, it's going to insert something at the position that the iterator is at. Same list, but 2 different results from calling add, depending on what object we're calling the add method on. Likewise, if we call the remove method, it's going to take from on the iterator, it's going to remove the last method, the last object, sorry, the last element of the list that was stepped over. Whether you stepped over it with a next or whether you stepped over it with a previous, it will be removed. So if you wanted to remove everything from a list that met a certain condition, you could do that with an iterator by first getting the iterator from the linked list and then running the code in the yellow box here. A while loop, so it's going to continue and go over the entire list. As long as there is another element for the iterator to step over, we're going to ask the iterator to step over that element and to tell us what it is. We're going to evaluate the element that we got back from the iterator, name in this case, and if the condition is fulfilled, so on the yellow block here, we've used a different font, Comic Sans. I'm really sorry about that. That's an affront to all humans. But the Comic Sans font indicates that we're doing pseudocode here. So if the condition is fulfilled for the variable name, whatever condition that is, this isn't proper Java code, but we're suggesting that you could put whatever condition you want. Is the string too long? Is it not long enough? Does it have the right character at the beginning? Is it alphabetized? Is it lowercase? Is it Korean characters? Is it Arabic characters? Does it have an emoji in it? Does it contain Patterson in it? Does it contain Dodger in it? Does it contain 2 zeros? Does it contain no digits? Does it contain duplicate letters? There are all kinds of conditions that we could ask about that string. And if it is met, then we can remove it by calling iterator.remove in the statement block associated with the if statement. And this will then remove the elements one by one. You just have to be careful about the remove method in the structure of your code because you can only call it one time for each element that you pass over. The remove method and the stepping over are tightly integrated. So you have to step over something before you remove it. And basically you can think of that as you have to evaluate an element before you remove it. If you try and remove something right after you add something, for example, you're going to run into some problems because it's not clear what you mean to remove if you add something and then you call remove. Do you want to remove the thing you just added, or do you want to remove the thing you just stepped over with next or previous? And so what Java will do is it will throw an exception saying that you must step over something before you can remove it. And so that'll be a runtime error if you run into it. And you'll get an illegal state exception for that. All right, so just a handful of stuff that you can do. First of all, we can get our next element. This is just reiterating some of the things we looked at. I don't want to belabor it, but if we have an iterator called iter, we can call next to go through our list. We can also call previous to move backwards. We can change the last element that we returned by setting it equal to something else. That doesn't remove anything, that doesn't add anything, it just changes it, so it replaces it. We can ask if there's another element. We can ask if there's a previous element, and if so, step over it. We can add something to in front of the previous where the cursor currently is, so adding Diana. And then we can do next and we can do remove if we want to remove something. All right, let's see. Actually, I kind of don't want to go through that sample program. What I want to do is I want to jump into talking about sets. All right, so that was a fast blow through of linked lists and lists with an introduction to the idea of iterators. And now if you think about it, there are actually a wide variety of ways that we have to do loops. We know about a while loop. We know about a for loop. We know about a do while loop. We know about doing fast enumeration in a for loop. And now we also know that there's a way that you can do loops using an iterator. So that's 5 different mechanisms for doing loops over different things that you can use in different situations depending on what the current design goals you have are, depending on what the design of your code is, depending on what you're trying to achieve. You may need any of them. I would say that the most common one that I use on a day-to-day basis is the for loop when I actually have the variables. So like for int I colon condition colon update I++. I use that most frequently. Then maybe the second most frequent one I use is the fast enumeration. The least frequently used one is the do while loop. That's the most rare, I think. But I have used all of them in my coding, and I do use all of them. All right. So in contrast to a list, what a set is keeping track of is a set is keeping track of a collection of elements. Well, that's not exactly in contrast because we also know that a list is a collection of elements. But the way a set thinks about the collection is different. It thinks about it in a way that's just whether something is present in a bag of data. If you think about like a list is like a coal car or a train with containers on it, where each one of the containers is hooked up in the train in sequence, and you fill each one of the containers with coal. Maybe a different kind of metaphor for a set is a really big bag, where you open the bag and you throw things in the bag, and all you care about is whether or not something is in the bag, and you're only going to put one of everything in the bag. And you can shake up the bag. The order doesn't matter so much. You're not worried about what the order is of your set. You don't want to maintain the order. You just want to know whether something is in there or not. And because you relax this requirement of having to keep track of the order of the boxcars, a set is more efficient in doing lookups and doing adds and doing iteration, all that stuff, because we can do some optimizations in the implementation that make it faster. but we lose some of the features of a list. And so this is why it's important to understand what kind of collection you need. Because if you don't need what a list offers and all you need is what a set offers, and you use a set in that situation, then your program is going to be more efficient. It's going to be faster. It's going to look and act more professionally. You're going to be able to change the world better. You're going to be able to change the world without using as much electricity. You're going to reduce climate change. So there are all kinds of ways in which choosing good designs matter. So a set, you're going to, let me just connect that. You're going to help climate change because you're going to be using less electricity. A set organizes its values in an order that is optimized for efficiency. And it may not be the order in which you add elements. In the code that we looked at yesterday, it actually was the case that it was keeping track of things in the same order in which we put them in, but that's not a guarantee. And as you get bigger sets, that won't hold. Inserting and removing elements from a set is faster and more efficient than with a list. Same interface, in terms of it being a collection interface, all the things that you can do with a collection, you can do with a set, just like you could with a list. It's just that the effects are different. So when you add something to a set, the effects are different than if you add something to a list. But both a set and a list can have something added to it. And that's what makes it match the interface. It has an add method. Sets don't allow duplicates. And there are two specific implementations that we can use in order to do this. One is called a hash set, and a hash set is based on an underlying implementation that uses a technology called a hash table. Hash tables are fingerprints. Hashes are fingerprints of data. A tree set uses an underlying implementation of a technology called a binary search tree. And a binary search tree is a little bit like the strategy that you use when you're playing 20 questions with someone, trying to separate out the world into things that are bigger than a bread box, smaller than a bread box, things that have feathers, things that don't have feathers. It's a little bit how a binary search tree works. We'll look at those later in the class. So a set implements those elements so that we can locate them quickly. And the way it happens in a hash table is that the elements are grouped according to collections. So if you have things that are in a set, for example, strings, each one of the elements that are in your set has a fingerprint, just like a person has a fingerprint. And just like we've learned that you can recognize a person by a person's fingerprint, and only by their fingerprint, you don't have to worry too much about their eye color or their hair if you have their fingerprint. There's a way that mathematically you can do the same thing with data. You can take a particular object or a particular string and you can represent it as a fingerprint, and you can keep track of its presence in a set by checking to see whether its fingerprints are present. And we can keep those fingerprints together in little buckets of like fingerprints that all start with the number 1. We can keep all those in a bucket. That's the idea of a hash code. So in order to be able to use the hash set implementation of a set, the object that's going into your set has to implement the method hash code. Hash code is something that returns a fingerprint for a particular object. You also must be able to compare two elements that are stored in a set because you have to know whether or not it's a duplicate. The way Java compares whether two things are equal is not using the double equal sign, because that's going to compare the reference. The way it's going to compare whether or not two things should be considered equal, remember whether things are, remember the court of law, the court of law analogy. We can think about people being equal in two different ways. We can think about whether they're the same person, meaning whether or not their DNA is the same, which is sort of silly because we don't really encounter that. But that's what a double equals is checking. It's checking to see whether two references are pointing to the same memory. Or we can check to see whether two things should be considered equal. Whether for a particular law, a man and a woman should be considered equal. For a particular law, whether a professor and a student should be considered equal. That's more of a human rights kind of equality. And so in Java, the way we do that kind of human rights style equality is we check the equals method. We ask whether two objects should be considered equal, even if they aren't literally the same method. An example of this might be you would like to consider two strings being equal, even if the cases differ, in which case you would have to write an equals method for a string substitute that would do that for you. As it stands, strings aren't considered equal unless each character is the same, both in intent and in case. Okay, fortunately, most of the objects that come with Java, like Java util classes, all have a hash code method implemented so that you can use them in hash sets without having to do any work. So for example, you can do a hash set of a string. So remember, if you implement a hash set of a string, what you're trying to keep track of is you're trying to keep track of a bag of elements, and the elements are each strings. So you want a collection of elements of unique strings. That's what you're asking for when you ask for a hash set of string. From a technical standpoint, the string has to implement hash code in order to be able to do that. It does, because we get that. That's what the people who implemented Java have done for us. Similarly, Rectangle comes out of the box with that. And actually, it turns out that hash sets themselves implement that. And so we can have a hash set of hash sets. That's something that's very powerful, and we do use things like that. So this third example here, a hash set of a hash set of integers, is keeping track of a set of sets of integers. So that might be, let's say that, what would be a set of integers? Let's say that each person had a collection of, let's see, what are something that you have numbers associated with? Let's say it's families, and you want to keep track of the ages of the people in a given family. And a family maybe has someone who's two people who are, well, that's not going to be a set. Okay, take it back. That's no good. Okay, I can't come up with a good example off the top of my head. A set of integers. I'll think of one and see if I can come up with a better one. Another analogy for what a hash set is doing, you can think about a collection of books, and that these books are all put into a set together. The order isn't going to be maintained for us, but what the underlying technology is doing, what the underlying hash set is doing, is trying to group your elements together, your strings, your rectangles, your books, according to those that are similar. And so here's an example of a bookshelf in which the books are grouped according to spine color. And so the analogy here is that spine color is like a hash code result. And we're going to keep those things that have the same hash code in similar locations. And because we know where to look for similar hash codes, we're able to find things faster. For example, if you knew that you were looking for a book with a white spine, you would be able to find that book faster in a bookshelf that's organized this way than if you had a bookshelf that was organized with things all over the place. Okay, in a tree set, the elements are kept in a sorted order, but a sorted order which the user of the set doesn't know about necessarily. Okay, so if a hash set is keeping things in terms is keeping books together in terms of the color of the spine, a tree set is going to keep things together in order of maybe the size of the book or the height of the book. Um, and they're kept in this sort of binary search tree order. It's not kept in a linear sequence. It's kept track of in a tree sequence, which we'll examine a little bit more in the future. So just like a tree set requires each of the elements, just like a hash set requires each one of the elements within it to implement the hash code method, a tree set requires each one of the elements within it to implement something called the comparable interface. Rather than in a hash set, what a hash code enabled us to do was to be able to tell whether two elements were equal. What the comparable interface enables us to do is to tell whether one element is greater than or less than another element. So hash code tells us equality, comparable tells us greater than or less than. Again, fortunately, because people who implemented the language knew what they were doing, most of the objects that come out of the box with Java have the comparable interface implemented for us, meaning that we can use them in a tree set, and we don't have to really think about whether or not that's comparable interface is present or not. But the reason why I exposed these things to you, the reason why I'm telling you about things that must be true, about things that are stored in a hash set or things that are stored in a tree set, and the things that must be true are that they must implement particular methods, is because before long, you're going to want to use a set. And what you're going to want to put into the set is an object that you've created. You're going to want to create a set of bank accounts, or you're going to want to create a set of I don't know, records of stuffed animals, or you're going to want to keep track of coffees that you've tried or coffee shops in Santa Barbara. You're going to want to keep track of some kind of set of things like that. And you're going to want to use the set from the Java collection framework. And you're going to find that Eclipse throws you an error because your object has not implemented one of these interfaces. Implementing the interface is easy, but trying to understand why you're having this problem is a little bit tricky. And so what I'm trying to explain to you is that you, in order to use some of these Java collection frameworks, what you're putting in them must have certain properties about them so that the rest of the infrastructure can actually do the work of keeping track of a set. Okay. One of the benefits of using a tree set is that when you do a fast enumeration, you get the elements out in order. So I said that a set doesn't keep track of the order in which you put things in. That's the contract of a set. It's a big bag. When you iterate over the set, you're going to get different results depending on whatever order the set decided to keep track of things in. And a hash set is going to give you back things in order of the hash code, but you might not have any idea what the hash code is of a particular element. So there is sort of a reason why things are coming back in a particular order. It just has nothing to do with the user of the set and what order they want. Likewise, if you use a tree set, the order that you're going to get things out of from your set is going to be whatever the natural order of the object is. So if it's an integer, you'll get them back in ascending order. If it's a string, you're going to get them back in alphabetic order. Regardless of what order you want them in, that's the order you're going to get them back in. This turns out to be a kind of a nice property because if you want to keep track of a big collection of things in a set and you know you're going to want to sort them anyway, you can use the implementation of the tree set and you're going to get them back in the order that the objects are naturally in anyway. What this means though is that a hash set is slightly more efficient than a tree set. And so you want to use a hash set unless you specifically need the ordering that the tree set provides. Again, why do you care about efficiency? Well, you want your program to run faster. You want your program to use less battery on your laptop when you're running your program. That's an impact of efficiency. In both cases, though, whether you choose an implementation of a hash set or whether you choose an implementation of a tree set, like this yellow box shows, you can store a reference to it in the higher level class, which is called a set. And both of those are going to implement the same methods, and they're both going to have the same contract that a set supplies. The implementation no longer matters. Once we assign it to a set type, we get those methods that are present in the set, and only the interface matters now. We lose access to any special methods that are only in a hash set or only in a tree set. And that sometimes is helpful, sometimes it's not. Depends on what you're doing with the code. All right. A couple examples of working with a set. Pretty straightforward. It looks a lot like working with a list. If we want to add something to our set, we get a reference to our set that we have already initialized. So this top yellow code, we need to have already initialized a set and assigned a reference to it with names. And here, if names contain strings, then we can add Romeo to it. If we don't like the fact that Juliet is in our set, we can remove Juliet. And this will be fine regardless of whether or not Juliet was present in this set already. Recall in Python, there were two different methods for removing things from sets, one through an exception and one didn't. In Java, we just remove things, and if it's not present, then nothing happens. If you care about whether it's present or not, you just have to ask first if it's present. Sets don't have duplicates, so if we were to add Romeo twice, the second add would have no impact. And that's just said that, removing an element that's not there is ignored. And if you want to know whether an element is present, you can use the contains method. If names.contains Juliet will return true if Juliet is present in the set. Capitalization matters, space matters, which particular characters you're using matters, it matches exactly. This isn't asking whether any string is present that contains Juliet in it. It's asking the set if the string Juliet occurs all by itself. So this isn't like searching for a keyword or something. This is asking if the entire atomic string Juliet is present in the set with nothing before it and nothing after it. Just like a list, a set also has an iterator. And if you don't want to use fast enumeration, because a set has an iterator, you can use fast enumeration. But if you want a cursor to do some kind of work with the set, you can use an iterator as well. And you can get that iterator by calling the iterator method on the set. So here we call names.iterator to return the iterator. We store it in an iterator type, also generic. We have to specify what it is that our list is iterating over. So our set is iterating over strings. Store that in a variable iter, iter. And we can do a loop that says while iter.hasNext, so while there's something else to step over, we're going to get it, store it in the name variable, and then this pseudocode here says do something with the name. Print it out, store it in a separate data structure, check it for some condition, whatever we want to do with that particular string. When we think about a list, the iterator is real natural. We think about it as a word processor and a cursor moving over the different elements. When we now bring the idea of an iterator to the collection of a set, we have to think more abstractly. We know that what an iterator is going to do is it's just going to move through all the elements in our set. A set doesn't really have a sense of ordering, but the iterator will still go through all of the elements in the set in whatever order the implementation is keeping track of them. And when we use a set, we're sort of giving up control over that ordering. We're saying, hey, implementation, however you want to keep track of these elements in the set is fine with me, the API programmer. I'm all good with that. I'm chill. Hey, fellow kids, listen to me using metaphors for being casual. Uh, YOLO set. You only live once, and so it's cool if you want to keep it in some other kind of order. All I need to know is that when I use my iterator, you are going to give me everything that's in the set back at some point. Before you tell me that the iterator no longer has anything left, the contract is that you will have gone through everything. Okay, let me stop for a second and see if we have any questions. That's a lot of work. All right, there is one. Faith says, does the iterator need to be the same type as the objects in the list? And the answer to that is yes. In this, it's not exactly the same type. It has to have the same generic. The generic in the iterator has to be the same type. So if the list is a linked list of strings, the iterator has to be an iterator over strings. And so when you declare it in the type, it has to have the same type in the generic, right? So I think in the way in which you ask the question, Faith, I think the answer is yes, right? It does have to be the same type. But formally speaking, the type includes the word iterator and the type includes the word linked list. So really the precise way of asking the question is, does the generic part of the type need to be the same as the generic part of the type in iterator and linked list? And yes, the answer to that is it does. And Eclipse will enforce that as well. So like what's great about a strongly typed language like Java is that if you try and do the wrong thing, Eclipse is going to complain and it's not going to let you do the wrong thing. It's going to say, hey, those are supposed to be the same. And so if they're not the same, then I'm going to stop you. So that's actually a real power of Java, which is why it's the best language out there. No bias, it's just true. All right. Man, I really like this stuff. This is great. The thing that you guys don't understand is that there's yet, if you continue studying this, you'll find that as you open the hood and you go behind the curtain on this stuff, there's more and more technology that's supporting all these things, and it's just beautiful. Like it's just so elegant to look at how a tree set is implemented and to look at the and why it's efficient and the way in which these hash code methods and the way in which comparable methods, the structure and the way that it all works together is really, really elegant. Like I wish I could communicate that well in an introductory class kind of like this because um, a lot of times you get deeper into a subject and you get kind of like, what the heck is going on? This is getting crazier and crazier. I don't know, like politics or something. But in Java in particular, and some other programming languages as well, as you learn more and more, you kind of get a greater and greater appreciation for what's happening here. And maybe a good analogy is a little bit like biology. I think that in particular Christian biologists, as they learn more and more about biology and they learn they go deeper and deeper into the cell mechanisms or how DNA interacts with proteins or the way a virus infects a cell. They just become more and more in awe with the wonder of the way biological systems are made, through creation and however God worked through creation to make these things. There's a little bit of that going on with these programming languages, although it's not a natural system. So I just want to encourage you that in as much as you find this stuff maybe overwhelming when you first see it, um, there's some really neat stuff going on underneath the hood here. All right. I'm looking at our time and I'm regretting the fact that we're running out of time because there's more to know, but there's also, we want to make sure that we get appropriately far in our work. So here's some some things that you can study to be well prepared. What I think is really good is to look at these data structures in context. And so if I were to do something next to try and understand these mechanisms better, is I would look at the example in the book of evaluating algebraic expressions with two stacks. Um, it's a really nice demonstration of why it is you might use a stack instead of a list. And it's a particular way of processing an algebraic expression that uses a stack. So if you can get your head around that, that is helpful for being able to understand these systems a little bit better. And in any event, you are going to have to spend some time in the textbook looking at things that we didn't cover in lecture. And yeah, so there we are. Let me switch over to in-game and see if there are any wrap-up questions. Okay, that's wrapping it up for March 5th. CS-030, Java Collections Framework. We'll head out and got class later today in another classroom. I'll head over there and stop broadcasting once I arrive. Let Dodger go. He can guard the classroom for us. Thanks, Dodge. Let's see, next class. Ending broadcasting for today, Westmont College, CS-030, March 5th, 2021. It's a pandemic, y'all.